These are the example exercises for Unit 1. During these examples, I will remind you how to set up your problems calculation-wise with variable lists, the formulas, and the work, and I'll remind you of what the point values are for them. And I'll also run you through the basic motion formulas as well as the more advanced time-dependent and time-independent motion formulas and how to calculate with those. First problem. What is the velocity in meters per second of a car that traveled a total of 50 kilometers north in 45 minutes? So, first things, looking at this problem, I'm looking for what is the velocity. And it's asking me to find the velocity in meters per second. So if I'm looking at this, I already have some variables that I'm going to need to convert, like the kilometers and the minutes. So first things first, I want to get a variable list. What is the velocity? It's asking me that, so I'm going to put that as a question mark. And it wants it in meters per second. I'll put that down just to remind me of what I need to do. It says the car traveled a total of 50 kilometers north. So my displacement is 50 kilometers, but since I'm using linear kinematics for this first unit, that north just helps me identify that yes, it is a velocity, it's a vector quantity, but I don't necessarily need it. And the time frame for this is 45 minutes. So, in order to do this problem, I'm looking for a velocity. I'm going to be using the formula d equals vt. It didn't mention any accelerations during this problem, so I know there's no accelerations present. And even if I used one of the more advanced formulas, the acceleration would be set as 0, so it would just be taken care of. So this is more of an average velocity. Now, before I start doing this problem, I find it easier to convert my variables first and then use them in the problem. So, first thing I need to do is convert 50 kilometers to meters. So, if I multiply by 1,000 meters per 1 kilometer, I will get 50,000 meters. I'm going to use that for my displacement variable. I have to convert my time variable now, so 45 minutes times 1 minute is 60 seconds, and that equals a time of 2,700 seconds. So I've got that variable and that variable as new ones. Let's actually just box them. Okay, so now I'm going to input my variables into my formula to solve for my velocity. I'm going to keep velocity as a v variable, as it's stated in the variable list. A lot of people like to change the variable they're looking for to an x. Try to avoid this. This is what you do in math class, but we're going to have variables that are x's, so you don't want to be changing your variable to something else. So let's input our information into our formula now. 50,000 equals v times 2,700. If I take that and divide both sides by 2,700, I get 50,000 divided by 2,700. I get a velocity of 18.5 meters per second. So now that we have our answer, let's take a look at point values. What would I assign for this problem? All calculation problems done in my class are worth 5 points total. Your first point is for listing out an accurate variables list, and that does include your new variables, this one right here and this one right here. So that's 1 point out of the 5. You get 1 point for listing the correct formula that you'll be using. You get 1 point for the correct answer with the correct units. You need the correct units with it or else it's not a correct answer. And you get 2 points for showing your work. And showing your work isn't just putting the variables into the formula and then spitting it out an answer. It's actually showing what you did to get that answer. As simple as what I just did here, dividing both sides by 2,700. that might be something that you just automatically know to do and can do in your calculator very easily, but you got to remember, I don't see your calculator. I don't see what you did, so in order for me to know that you understand what you're doing, you need to show your work. Plus, when it comes finals time and you start to review these exercises, you want to see what you did, because a month from now you might not remember exactly what you did to get that answer. Okay, your next question. A car accelerates from rest to 28 meters per second in 7 seconds. What is the acceleration rate? So first things first, it's looking for the acceleration rate. So I'll write that as A equals question mark. Now, I'm looking at it and I see my other variables. I see time of 7 seconds. And now's the part of physics that a lot of people don't like, where you have to actually interpret what's going on. A lot of times it doesn't just spell it out for you. So a car accelerates from rest, which means it started at an initial velocity of 0 meters per second. And it accelerates from rest to 28 meters per second. So final velocity of 28 meters per second. So a lot of times you'll see that from rest. That means initial velocity is 0. So you have to make sure you interpret that correctly. Now I'm looking at this, I see velocities in meters per second, a time in meters per second, which means my acceleration will be in meters per second squared. So I have my variable list ready. Next thing I want to do is see, I'm solving for acceleration. I have initial and final velocity and time. The formula that best fits this is A equals VF minus VI over T. That's the formula that fits this exercise the best. So now I'm going to put in my variables, again without the units, because sometimes the units will look like variables and you might get confused. So A equals 28 minus 0 over 7. So when I do this, 28 minus 0 is 28 divided by 7. I get an acceleration of 4 meters per second squared. Remember, it's always good to put your answer in a box when you're done so I can identify it. A lot of times, as you'll see later on, we're going to have examples that have multiple formulas to get to the answer. So when you put your answers in a box, it helps to identify where they are. Alright, a car accelerates at a rate of 2 meters per second squared. If the car starts from rest, there it is again, starts from rest, how fast will it be traveling after 5 seconds? How fast will it be traveling? So two variables right there that aren't given in the problem, but I need to understand. So let's start out by looking at this. A car accelerates at a rate of 2 meters per second squared. If the car starts from rest, initial velocity is 0 meters per second. How fast will it be traveling? Final velocity after 5 seconds. Time equals 5 seconds. So again, acceleration's in meters per second squared, initial velocity is in meters per second, time is in seconds, so my final velocity will be in meters per second. So I'm looking at this one again, same formula as last time. Acceleration equals final velocity minus initial velocity over time. So 2 equals final velocity minus 0 over 5. Now I multiply both sides by 5. That will cancel out this 5. And I have 10 equals VF minus 0, or VF equals 10 meters per second. Box my answer. Now just a reminder, 1 point for the variables list, 1 point for the formula, 2 points for the correct work, and 1 point for the correct answer with the correct units. If I had gotten this answer wrong and I had maybe divided by 5 up top here, I got 1 point for my variables list, 1 point for my formula, and 1 point for the work. I still passed the question with a 60% because I did kind of know what I was doing, but I didn't get the correct answer, so I'm not going to get full credit for it. Okay, so on to some more advanced problems. A car is traveling down the road with a velocity of 5 meters per second. The speed limit increases and the car accelerates at a rate of 2 meters per second squared for 3 seconds. How far did the car travel during this acceleration? So I'm looking for a displacement. So let's start by listing out our variables. The car is traveling down the road with a velocity of 5 meters per second. That's my initial velocity. The speed limit increases, meaning I'm going to have a higher final velocity. And the car accelerates at a rate of 2 meters per second squared for 3 seconds. How far did it travel? Now I'm looking at my units and I see that my displacement will be in meters. So I have an initial velocity, an acceleration of time, and a displacement. Now a lot of people might be tempted to use this formula, but I can't because there's no acceleration in there. That's for an average velocity. That won't give me the variables that I need or the calculation that I need. So make sure if something is accelerating, you don't use that. So I'm actually going to erase that now because I don't want it. Okay, the correct formula that I'll be using is D equals VIT plus 1/2 AT squared. That is my time-dependent motion formula, and that will give me everything that I need. If you look, all my variables are in there without any variables that I don't want. So let's start plugging stuff in. D equals 5 times 3 plus 1/2 2 times 3 squared. Be careful, that square right there, a lot of times people put the square around the 1/2 AT and they square the whole thing, but it's only actually the time variable that's being squared. Okay, so now it's just a matter of punching in these numbers into my calculator, but I'm not going to do all of it all at once. I'm going to write out these smaller sections that I have. So 5 times 3 is 15. Plus, now 1/2 times 2 times 3 squared. 3 squared I know is 9, times 2 is 18, times 1/2 is 9. And then I'm going to finish the problem. 15 plus 9 is 24. And that is written in meters, and I will box my answer. So you see that initial velocity in time, and then here's the initial velocity that I was traveling, and then the acceleration is how much I gained on top of that. So if I'm traveling at 5 meters per second and then I accelerate, I'm still doing the 5 meters per second, but I'm also doing the additional velocity after on top of it because I accelerated. A car travels 750 meters while accelerating from 5 meters per second to 10 meters per second. At what rate did this car accelerate? So that's what I'm looking for, acceleration. But it goes from 5 meters per second to 10 meters per second. That's a positive increase. This is a positive acceleration. So this car is speeding up. But let's look at the variables that we have. We have a displacement of 750 meters. We have an initial velocity of 5 meters per second and a final velocity of 10 meters per second. So looking at this question already, I can see that I don't have a time variable in here, and it doesn't mention it, so I'm not necessarily going to try to solve for it. But if I look at it, I do have everything I need for the time-independent motion formula. Okay, this one does not depend upon time, just an initial and a final velocity and acceleration rate and how far you went. There's nothing to convert in here. I see that my velocities are in meters per second, my displacement's in meters, so I will have an acceleration in meters per second squared. So let's start to put in the variables. 10 squared minus 5 squared. Remember, it's the variable that's being squared, so the square has to be inside that parenthesis. That negative is going to be important. You don't want to square it out. Equals 2 times my acceleration times my displacement of 750 meters. So 10 squared is 100 minus 25. If I had squared out that negative, I'd be adding a 25 now. Equals 1500 times A. So 75 equals 1500 times A. If I divide both sides by 1500, I have acceleration equal to 0.05 meters per second squared. Now that looks kind of small. I've been dealing with larger numbers throughout this whole thing. 750 meters, 5 and 10 meters per second for velocities. To have an acceleration that's 0.05 meters per second squared, that doesn't seem like the correct answer. However, if I look through my math, I have 10 squared, let's get the pointer, I have 10 squared, I have 5 squared, I have 2 times 750, I have 100 minus 25, 1500. Everything checks out for this to be the correct answer. So I know that I have the correct answer here because all of my math works. If I look back at this problem, it's 750 meters. That's over half a mile to go from 5 meters per second to 10 meters per second. And 5 meters per second, if I do a quick conversion here, is only 11 miles an hour. 10 meters per second is 22 miles an hour. So I went from 11 miles an hour to 22 miles an hour in half a mile. That's not a big increase. So it's not just a matter of crunching out the numbers and getting an answer, as it is understanding the actual problem. I went a very far distance and barely changed my velocity, so that works. Okay, last example, and this one is the more difficult of them from this example set, and it has multiple steps, so I wanted to get through one of these with you. And I may have to erase at some point to fit it all in, but let's get through it. A car is stopped at a red light. When the light turns green, the car accelerates at a rate of 2 meters per second squared until it reaches 20 meters per second. The driver then sees another red light ahead and applies the brakes, slowing the car to a stop at the light at a rate of -4 meters per second squared. How far apart were the red lights? So let's think about this problem without the numbers. I'm stopped at a red light, light turns green, I hit the gas, I accelerate, I see another light, I let go of the gas and hit the brake and slow down to a stop at the next light. It's kind of like driving in the city. So there's a couple of things in here that we're going to pick up along the way that are important towards this problem. First, let's list out our variables. This is a two-stage problem. There's the first initial acceleration and then the last acceleration that brings it to a stop. So we've got to break this up into two parts. So the first part is I'm going to look at that speeding up part, and I need to get my variable list down. So I have initial velocity equal to 0 meters per second. I was at rest at a stoplight. When the light turns green, the car accelerates at a rate of 2 meters per second squared until it reaches a final velocity of 20 meters per second. The driver then sees another red light ahead and brakes at a negative acceleration rate. I'm going to start setting up kind of a twofold problem. So at the point where I hit my brakes, that becomes a new problem with a new initial velocity of what my old final was, 20 meters per second. Because at that point of my final velocity, 20 meters per second, I then hit the brakes, that becomes my initial, and then I come to a stop at the next light, which makes this now 0 meters per second, coming to a stop, and an acceleration of -4 meters per second squared. And for both of these, I want to know how far apart the red lights were, so I need a distance for both of these. I'm going to add them together later on. So let's look at the formula that I need. I have final initial velocity, acceleration, displacement. I don't have time, so I'm using VF squared minus VI squared equals 2AD for both of these. I'm going to start with the first half and see how far I go. So I'm going to do my work down here to make space. 20 squared minus 0 squared, and yes, it is important to show that, equals 2 times my displacement. So 20 squared should be 400. minus 0 equals 4 times d. So if I divide both sides, I have 400 equals 4d. If I divide both sides by 4, that cancels, and I get a displacement of 100 meters. That's my first one. So maybe I should label this D1. My second one, I'm going to use the same formula. Vf squared minus Vi squared equals 2AD. And I'm going to plug in these variables. Now, I've got to remember, I've got a final velocity now of 0 squared minus an initial of 20 squared. Like the last problem, this is where it's important that that negative stays in there. Equals 2, a negative 4 acceleration, and a displacement of d. So 0 minus 400 equals negative 8d. So negative 400 equals negative 8d. Divide both sides by negative 8. Cancels. Divide by negative 8. 400 divided by negative 400 divided by negative 8 gives me 50. So I'm going to label that D2 because that's my second one. Now that I have both of those in, I just have to add them together. D1 plus D2 equals my D total. So 100 plus 50 equals 150 meters. There's my answer. My total distance is 150 meters. The great thing about this problem is twice as much work for the same amount of points. Again, the variables list, there's 2 of them now, so I got to make sure both of these variable lists have the correct information in them. There's twice as much work. I got to make sure it's all correct. 2 formulas. Sometimes you could list this all in one variables list. If I wanted to do VI1, VF1, VI2, VF2, to establish the beginning and the second, and an A1 and an A2 and a D1 and a D2. But I like to set it up as multiple different problems, and you'll see during tests a lot of times I'll set it up as a part A, part B, part C, part D, in order to make it a little simpler and not as confusing. So, for each unit we will do some example problems. Hopefully these help you get through your homework, and I would take these every now and then and maybe take a picture of it or print it, add it to your notes, or just review it over and over again. So we'll be dealing with some more advanced problems during our meeting on Wednesday.